application, they set out a motion problem. The second one is area between curves, right? So I want to show you that where the rise of Riemann sum is coming. Already, the Riemann sum is motivated from the area problem, so it is kind of an easier example, but I'll pretend and still pull out that interpretation. But you will find that the setting is slightly different. So this is what they mean by area between curves. Are you having fun with the shape? That's right, yeah. So I'd like to give a little bit of, just like we did in, velocity problem, I want you to give a little bit of analysis. Some of you already can see how to do this problem quickly, but this is kind of a little prototype of example of analysis. From A to B, we want to calculate the area of this region, right? So here's one approach. So I'm going to divide this one into n pieces. N can be, 100, 200, very, very many pieces. Then here is one interval where left endpoint is x sub k, xk minus 1. Right endpoint is xk, right? So draw the vertical line on that. This is application problem. Even though it's geometry problem, you have to be a little bit rigorous. I'm going to be a bit sloppy here with approximation and all that. So if you do the vertical, let's use rectangle to estimate this thin strip of the gray part using, maybe you're going to use right endpoint. So if I use right endpoint here, draw a horizontal line, and use that right endpoint and draw a horizontal line. So there you can see this rectangle. Area of the rectangle is not quite the same as area of the gray area. There is a little bit of underestimate and overestimate and all that, but it's similar to each other. So if I zoom in, the picture looked like this. This seems like actual region, and we're using this rectangle in here, right? Area of this rectangle seems like approximately same, ignoring the tiny pieces. So let's calculate. Yes. It is because I'm just trying to show you that how the analysis that I mentioned in many areas of application of the Riemann sum, the three we're about to go through, and many more, uses this idea, because situation over here is different from situation over there. To analyze a different situation, you have to look at individual slide, and it's one idea. It's not the only idea. You can go in and do this thin horizontal slice, and you can look at the problem that way, and sometimes that's a better way than the vertical strip. So it's just an example. So what is the width of this? What notation do we use for width of this rectangle? Delta x, right? Let's say it was regular partition. We just want to measure this one, so you don't have to enter irregular. We're not defining anything. How about the y-coordinate of that using what's given? We don't have a formula. We only have f of x and g of x. That's all we have, right? What do you think the y-coordinate of that point is in terms of what is written here? Right. That's not the height. That's not the y-coordinate of that. Y-coordinate of that. Y-coordinate. F of, right? X is not quite right. You need subscript. What do you plug in here? xk or xk minus 1? xk, we use right endpoint right here, right? So it should be xk. Alright, that's y-coordinate. What is the y-coordinate down there? G of xk, right? So, if you have a top y-coordinate and bottom y-coordinate, how would you calculate the distance between these two y-coordinate? Top y-coordinate, right? Minus bottom y-coordinate, right? This is actually true even if they are across the x-axis or completely below the x-axis. No matter where they are, if you subtract the bottom y-coordinate from the top y-coordinate, you always end up at positive or 0. So this is going to be always a positive number. They didn't want signed area. They actually want this one There's a positive area, right? That's one thing slightly different from what we're doing with the definite integral. I didn't multiply it, I subtracted it. Yeah, right. Correct. That's correct. Now, how do you get the area of this thin rectangle? Right, width times that. So I'm going to write it like this. F of xk minus g of xk, right? Top y coordinate minus bottom y coordinate times delta x. That's the one area of this thin slice. If you add them all up, that must be a good approximation, right? Of this whole region. Fair enough? So now we enter. The whole area seems like approximately equal to all this thing, f of xk minus g of xk, right? Multiplied by delta x. You add them all up. Okay, starting from the first interval to nth interval, right? So that must be the same. Because we want the area of this region, rectangular region, you have to multiply the height by the width. Width is the delta x. That's right. Any other question? All right. Here's an example of it. So you analyze a problem, and it looks like a Riemann sum, right? Here's why. Because you have delta x appear there. Everything else that is multiplied to delta x is all in terms of single variable. What is that variable? Xk, right? An xk. Then this is a Riemann sum. This is not equal to, but approaches to, right? Which integral? This whole interval from a to b to that delta x becomes a dx, right? Everything that is in front of delta x in terms of xk changes to in terms of x. So here's f of x minus g of x. Find an antiderivative of f of x minus g of x. Plug in b and a. That's the area in between the two curves. All right? So this is an example of analyzing geometry problem down to thin pieces and formulate it as a sum. And it happened to be the Riemann sum. Whenever you have a Riemann sum, you can pass it to definite integral. Once you have that, if you know the antiderivative, there's a real quick way to compute that definite integral. What is that? Fundamental theorem of calculus, part 2. Make sense? All right. However, you can look at it as in a slightly different way. If that's true, that after you analyze it, it seems like you can look at this problem like that. AB f of x dx, that will be the area of the top curve all the way down to x-axis, right? That's what that measure. Remember the very definition of a definite integral? From the top curve, one curve, all the way down to x-axis, right? That's what this one measures. Minus a to b, g of x, that measures the area from g of x all the way down to x-axis, right? If you subtract that too, do you see that you're left with that region right there? So that's the picture that I have probably in the last part. It's down there. The integral fx will be measuring the area from f of x down to all the way down to x-axis, right? Minus this one, g of x down to x-axis. This part is common for both cases. If you subtract off, you're left with the middle one. So you can also understand that a lot easily by looking at this formulation. This one measures that area right there. It's easy. Once you have that, using the linearity, you can enter inside the integral like that. I hope that's logical enough. So there's an easier way, but I chose that path to introduce the analysis that involves a Riemann sum, or that gives you rise to a Riemann sum. All right? So formula is that this. To calculate the area, top curve minus bottom curve, a to b. That's the answer. Make sense? Y coordinate difference. All right. But it can happen, something like this can happen. All right, here's A. Let me use dotted line. Here's B. dotted line. One curve f of x goes through like this. G of x at the beginning was below. This is f of x. Y equals f of x. Curve below was there, but in the middle they cross each other. Y equals g of x, right? So up to here, f of x is at top, but after that point, f of x is below. So if you want area in between these two regions, we're probably talking about this area here, right? So if you just subtract f of x and minus g of x, this will count as a negative area because they're upside down. Therefore, if you want real region and area between the curve, you have to figure out where they crosses and calculate A to C first, knowing which one is at the top, which one is the bottom, and from to C to B separately, knowing which one is at the top and which is at the bottom. Calculate this both area as a positive region and add them together. Hope that makes sense. So here is an example. It's already challenging enough to, if you read about this one. So here it is. Your first exercise is that you sketch the graph and figure out the situation. Which one is at top and which one is the bottom. And it didn't even give you A and B, and figure out what those A and B are. So this is exercise number 2. 3. Number 1, sketch the graph and figure out top curve, top and bottom curves. And also A and B. Where is A and B? Right? Once you have that setting, you can plug it in and calculate. Sorry about not giving you enough time. Yes, go ahead. Alright, that's to sketch the graph. And do you see that the region they're describing enclosed by this parabola and the line? Right, do you agree that that region they're talking about is this one? Agree? If you look at other region, it's opened up to infinity, and every other thing it's infinite regions. So that's a sketch on the graph and a sketch of the region. How about this A and B? How are you going to find that A and B? Do you kind of locate an A and B, not numerically, but roughly in this picture? Do you see where the A and B are? Right, this person here, that would be A, that would be B, right? So that's where x equals A is. X coordinate of that point, that x coordinate of that point would be B. So once you have that, you can formulate. So how do you calculate A and B? They cross this intersection point. You set these two graphs equal to each other, right? So what are the graphs? X squared plus x minus 5 is equal to 3x minus 2, right? So I'm doing this quickly. If you move everything to one side, it's negative 2x minus 3 equal to 0. So this is x minus 3. X plus 1 equal to 0. So you see that what A and B are? A is negative 1, right? And B is positive 3. Alright? So finally, the formulation, and then I'll let you go. From negative 1 to positive 3, right? And dx. And what is the top curve and what is the bottom curve? Linear minus quadratic, quadratic minus linear. What is the answer? Top, right? This is above in that region. If you look at one vertical line here, you can see the top curve passes through the linear and bottom coordinate passes through quadratic, right? So here's a 3x minus 2 minus quadratic x squared plus x minus 5. This will give you the answer. Rest is to simplify and integrate polynomial. It's fairly simple. And the book has the complete answer to that too. Alright? So I'll stop here and